In this lesson, we're going to look at what surds are. So let's dive in. Irrational or non-rational numbers are numbers whose value have no ending. So let me start by saying that we have two major types of numbers. We have the rational numbers and non-rational numbers. The number is said to be rational if it has an exact value or if the value has an ending. So if we are computing or calculating, let's say 14 divided by 2, discover that the answer is 7. So 7 is an exact number. Or let's say 1 divided by 2, which is 0.5. 0.5 is an exact number. If you compare these two, let's say the value of pi, which is equal to 22 over 7, we have 3.142 on and on. So you see that this particular number continues indefinitely. If you keep calculating, the value you're going to have will keep going on. So it doesn't have an ending. Another example is the value for root 2. If you push the calculator, you discover that the value keeps going on, root 3, root 5, and on and on. So values like this that values of such numbers that do not have exact value or that the values have no ending are said to be irrational or non-rational. On the other hand, values that have values that are exact or have an ending are said to be rational. The examples are root 2, root 3, root 5. So we'll talk about examples. So we're talking about examples of irrational or non-rational numbers, and we say that irrational or non-rational numbers are numbers whose value have no ending. So examples are root 2, root 3, root 5. The square root of all non-perfect squares are irrational. Likewise, their multiples and fractions. This brings us to what perfect squares are. Perfect squares are simply the squares of numbers. Like if you any number that multiplies itself, or the square of any number is a perfect square. So 2 times 2 will give us 4. 3 times 3 is 9, and then 5 times 5 is equal to 25. So the square root of such numbers, when a number multiplies itself, like the square of a number, so 5 squared is equal to 5 times 5, which is 25. The square root of 25, the square root of 9, the square root of 4 gives us 2, give us the number that was squared, which is 2, and square root of 9 is 3, square root of 25 is 5. So 2, 24, 9, 25 are said to be perfect squares. So the square root of perfect squares will give us rational numbers, which is exact figures. On the other hand, the square root of non-perfect squares, so if you have 26 is not the perfect square because no number multiplied itself to give us 26. Rather, you're going to have 2 times 13 to give us 26. Unlike when 2 times 2 multiplied itself or 3 multiplied itself to give us 9, and then the square root of 9 gives us 3. So since no number multiplied itself to give us 13, this is a non-perfect square. So the square root of 26 will give us value that is irrational in the sense that it's not going to be exact. The value will not have an end. It will continue indefinitely. So if you punch your calculator, you're going to have something like, let me assume because I'm not my calculator here. So let's say 7.841 and on. So, and we have other figures like square root of 18, square root of 11, square root of 13. So square values of such square roots, they give us irrational numbers. So that's what this part of this sentence is saying. So the square root of all non-perfect squares are irrational. Likewise, their multiples and fractions. Also, pi is an example of irrational numbers. We know that pi is a constant which has a value, and of course when we look at area of a circle, we always come across pi. Area of a circle is pi r squared, and the perimeter or circumference of a circle is 2 pi radius. The value of pi is equal to 22 over 7, and which is equal to 3.1421. Also, pi is an example of an irrational number. So we refer to the square root of non-perfect square as surds. So we classify the square root of all non-perfect squares as SURD. So when we look at what we have here, root 26, root 18, root 11, root 13, and all the rest, and other non-perfect squares, the square of such numbers, they are all classified as SURD. So SURD has its own basic rule of operation with addition, subtraction, multiplication, and division. Rules of SURD. When we're looking at SURDs, we need to understand that SURDs are governed by certain rules. Like the statement here says, SURD has its own basic rule of operation with addition, subtraction, multiplication, and division. So when we're looking at SURDs, we must understand that at the root of it, there are rules that govern how we carry out operation on SURDs. So let's look at the basic rules. The first one is addition and subtraction rule. In addition and subtraction, root a plus root b is equal to root a plus root b. This is to say that we cannot add two SURDs that have different roots. So if we have root 2 plus root 3, as we can see here, let's say root 2 here stands for root a, root 2 here stands for root b. Because the roots are not the same, the value under the square root signs are not the same, that means it will still be equal to root 2 plus root 3. We cannot carry out basic addition. Just like algebra, if you have a plus b, you can't add. A plus b is simply a plus b. But if it's a plus a, since they are like terms, you can add. So this will give us 2a. So exactly what we have. This is the same thing except, but in this case, we have a plus root b, which is equal to root a plus root b. We couldn't add because the figures or the letter under the square root signs are not the same. So what the rule of addition and subtraction rule states that if the roots are not the same, that means they are equal, you can't add, you can subtract, just leave them like that. But when the roots under the square root sign, when the figure or the letters under the square root sign are the same, then you can add them just like you add in algebra, which in this case a plus a equals to 2a. So if the roots are the same, root a plus root a, then since the letters, or which by the time we start solving, the figures are the same or will be the same, then what we do, we can add them together because they are the same. So root a plus root a, so this is like 1 root a plus 1 root a, and that will give us 2 root a. And root a minus root b, what is applicable under addition is also applicable under subtraction. So root a minus root b, since the letters are not the same, just as in algebra, it will give us the same value, root a minus root b, which means we couldn't subtract because the letters in this case are not the same. But later on, we're using numbers instead of letters, and even at that point, if the numbers are not the same, we are not going to add and we are not going to subtract. We will not be able to add, I will not be able to subtract because the numbers under the square root signs are not the same. But what if they are the same, which in this case they are root a root a, then we can subtract because the operation is subtraction. So 4 root a minus 2 root a is like 4 minus 2, so that will give us 2 root a. So 4 root a minus 2 root a is equal to 4 minus 2, which is equal to 2 root a. This is same thing as 4a minus 2a. What do you do if this were an algebra? So what you do is 4a minus 2a is 4 minus 2 give us 2a. Just like saying if I have 4 apples and I give someone 2 apples out of the 4 apples I have, what would be left? I would have 2 apples left, so which is why we still have 2a there. So that's for the addition and subtraction rule. Now let's look at multiplication rule. Multiplication rule is basic. So root a times root b, simply when we have root a times root b, this is equal to root a times b. That's all. Which so if we have 2 root e times 3 root b. Of course, the coefficients will multiply themselves, and then the variables also multiply themselves. When I mean coefficients, I mean the numbers before the letters. So 2 times 3 is the coefficient. These are the coefficients, 2 times 3, and then root a times b. This one will multiply themselves. So a times b multiply themselves. So at the end of the day, you're going to have 6 roots a b. So that's for the multiplication rule. Then division rule, root m over n is also equal to root m over root n. So if you see something like this, root m over root n, this is also equal to root m over root n is also equal to combined root of m over n. So either way, this is true and this is true. So that's for the division rule. So we're going to take some examples. Or these examples that we have here, we're going to apply these rules on them, and take that will really show how we go about calculating or solving problems on SURDS. So the first one says root 2 plus root 3. But to carry out simple operation of addition, but in this case, like the rule we have here, since the roots are not the same, this is 2, this is 3, they are not the same, we can do nothing about this addition. So it will be equal to what we have on this side of the equation, root 2 plus root 3, as and this will base this rule, root a plus root b is equal to root a plus root b. That's all. Number 2 root 5 plus 3 root 5, 2 root 5 plus 3 root 5. So we can only add algebraically, just as we can only add just as we do if it were an algebraic equation or an algebraic expression when the roots are the same. So just like when I was explaining, I used something like I said, if we have 2e plus 3e equal to 5e. So since the letters are the same, or we say like terms, but here we say like roots. So if the roots are alike, then we can add just as is possible under algebraic conditions. But if the roots are not the same, like what we have here, then we cannot add. It's going to be equal to what you have here. So 2 root 5 plus 3 root 5, since we have like roots, so 3 plus 2 give us 5, and that will give us 5 root 5. Number 3, 9 root 2. 9 root 2 minus 5 root 2. So same condition here, we have like roots, so we can subtract. 9 minus 5 is 4, then that was 4 root 2. Number 4, 3 root 3, 3 root 3 times 8 root 3 times 8 root 3. Of course, this will give us 3 times 8, 3 times 8, and then root 3 times root 3. Okay, so this will give us 3 times 8 is 24, and then 3 times 3 is 9. So this is 9 is a perfect square, so we can get the exact value for it. The square root of 9 is 3, so 24 times 3 is equal to 24 times 3. This is 12, 72, and 72. Number 5, 6 root 3 times 8 root 3. Oh, number 4, 6 root 3, 3 root 3 times 4 root 2. 4 root 2. 4 root 2. Let's get the exact value for number 4. 3 root 3 times 4 root 2. 3 times 4 is 12. So 3 times 4, 12 root Root 3 times root 2 will give us 3 times 2. And this will give us 12. 3 times 2 is 6. So since 6 is not a perfect square, we don't need to get the exact value of 6 because it's irrational. So go on indefinite. So we're going to leave it in this form. 12 root 6. Number 5. 6 root 3. 6 root 3 times 8 root 3. This is 6 times 8 root 3 times 3. 6 times 8 is 24 root 9. That's equal to 12. 24 times root 9 is 3, which is equal to 72. Number 6. Number 6 root 60. Root 60. For this particular issue, this particular example, if you have to simplify this, it means you need to write this in the form of in this form as two numbers that we multiply together to give us 60, and the rule is that one of those numbers must be a perfect square such that you can get the square root of that particular number, and the other one will be in surd form. So 60 is gotten by, so we have 12 times 5, which is a 60, and then we have 12 times 5 is a 60. We have 30 times 2, which is a 60. None of them here is a perfect square. 12 is not a perfect square. 5 is not a perfect square. 30 is not. 2 is not. So we cannot use any of this. So what other number will give us 60? Let's look at 15 times 4, which is 60. So from the rule of surd, when we are simplifying a number, like in this particular example, 60, where we must write 60 as a factor of two numbers. That means what I mean by factor of two numbers is that two numbers that multiply themselves to give us 60, or the factors of 60 get two factors of 60. Now, one of those factors must be a perfect square. So this one will give us 60, these two factors will give us 60, but we couldn't use any of these two factors because none of them is a perfect square, and the rule is that one of them must be a perfect square. So we're going to go with this one, 15 times 4. 15 times 4, that's square root of 15 times 4. So of course this means root 15 times root 4. So this is why the rule says one of them must be a perfect square, so that, which means, as you can see, this is root 4. Root 4 is a perfect square, and we can get the exact value of this, but this is a non-perfect square, so this one will remain in this form. So root 4 is equal to 2, that's root 15 times 2, which is equal to 2. Root 15 times 2 is equal to 2 root 15. That's the final answer. So always follow the rule. Whenever you are looking for the factors of a number under a square root sign, make sure that the two factors are equal. One of them must be a perfect square, such that you can get the exact value of that perfect square, and then the other factor can remain as a non-perfect square. Number 7, root 80 plus root 20. Root 80 plus root 20 plus minus root 45. So the same thing here. So we're going to get two factors of 80, and factors of 80, we have 40 times 2. For factors of 80, we have 40 times 2 to give us 80, and we have 10 times 8 to give us 80, and also what other, we have 16 times 2. 16 times 2 gives us 16 times, no, we have 16 times 5 to give us 80. So now, from what I explained earlier when I was treating this example, if you go by these two factors, although each of them gives us 80, but we're going to make use of this only because if you look at here, no, this one is not the perfect square. This 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 one is a perfect square. So one of the factors must be a perfect square. So here we have 16 times 5 equals to 18. And here we give us roots. So 80, you simplify 80 to give us 16 times 5. Let's simplify 20. Factor of 20 is 10 times 2, 20. And then 5 times 4, 20. 20 times 1 plus 20. Out of which only this one has one of the factors as a perfect square. So we take that one. That will give us 5 times 4 minus square root of 45. 45 will give us 9 times 5. 9 times 5. 9 is a perfect square. 9 times 5. So let's simplify. Square root of 16 times 5 is equal to the root. 16 times root 5 plus root 5 times root 4 minus root 9 times root 5. And this is equal to root 16 is 4 root 5 4 root 5 plus root 4 is 2. So 2 times root 5 is equal to 2 root 5 minus square root of 9 is 3. So this is 3 root 5. So since we have like roots, all the roots are the same, root 5, root 5, root 5, we can carry out the operation of addition and subtraction. So 4 root 5 plus 2 root 5 will give us 6 root 5 plus 4 plus 2 is 6. 6 root 5 minus 2 root 5 will give us 3 root 5. Root 5. Number 8 root 2. Root 2 times root 6. 2 times 6. That will give us root 4. Number 9 root 35 over root 5. From our division rule, which we still have here, this is equal to, so what we have, this root 35 over root 5 is this form, root n over root n. So this form is equal to this form, this form is equal to this form. So if we have, since this is what we have, we're going to put it this way, root 35 over 5. Why? Because we can't get the exact value for root 35, we can't get exact value for root 5. So root 35 over root 5, root 35 over 5, 5 over 1, 5 over 7. This is equal to root 7 as answer. In number 10, root 17 over 4. Root 17 over 4. So this form is equal to this form here, root n over n. So what would it be equal to? To be equal to this form. It's equal to root 17 over root 4. Now one of them is a perfect square, which is this. This is equal to root 17. Root 17 over square root of 4 is 2. So that's the final answer. Root 17 over 2.